University of Bahia, and you can see his title on the screen. So thank you very much, Dirk, for accepting the invitation.
Okay, well, thanks a lot for inviting me again. I think it's the second time that I'm speaking here. And so anyway, so as you can see, so this time I talk about something, I guess, a little bit more classic. And I'm sure that many of you in the audience know this topic quite well, but I prepared the talk so that the people that are not expert in it should have a chance to understand it. So the results will be new, but probably many of the heuristics I give are maybe not new for the experts. So I'm sorry for that. So you can relax today a little bit. But anyway, okay. So as you can see, the title of my talk is Joint Fluctuations of Current and Occupation Time for the Exclusion Process Out of Equilibrium. And this is joint work in progress still with Tertuliano, Franco, and Tiecheng. So both are from UFBA. There's a professor there, and Tiecheng is now doing a postdoc. Okay. So, I mean, I guess quite standard, I should start to talk about the exclusion process. 90% of you know what's the exclusion process, but still, I guess I should shortly say some words about it. So what is the exclusion process? So basically what you imagine is that you have some graph ZD, some general graph, and on this graph you consider a bunch of random walkers. Yeah? And these random walkers evolve essentially independently on this graph. Yeah? However, they must respect the exclusion rule, meaning that two random walkers are never allowed to be at the same site at the same time. Yeah? So this is kind of how they interact. They're independent, subject to the exclusion rule. Once they want to jump on top of each other, they feel each other. Yeah? So it's really relatively simple. So let's say here you have, let's say on the one-dimensional line, maybe you have no particle here, no one particle here, no particle. There's a particle, there's a particle, there's a particle. Maybe there's no particle here, no particle here, but there's a particle here and no particle. So then all of these particles, they want to do random walks. You know? So let's say nearest neighbor random walks. So for instance, this guy may want to jump to the right or to the left at a certain rate, say rate 1 with probability 1/2. Probability 1/2 to the right, probability 1/2 to the left. If he wants to do it, well, he simply does it. So afterwards, he will be here, and this site is in. Yeah. So if this guy in the middle wants to jump to the right or to the left, so it's one of its exponential clock rings, then the jump is simply suppressed. So nothing. So this is where the exclusion rule really kicks in. Yeah. So formally, what is happening that for each time t, the configuration at time t, eta t, was what can take two values, right? At each side, there may be either no particle, 0, or there may be a particle, 1. Yeah. And we will consider this exclusion process on the line on Z, in the discrete line Z. Yeah. And so for now on, I want to say that these random walkers, they all jump at rate n squared. So instead of jumping at rate 1, all the walkers jump at rate n squared, where n is a parameter of the model that will later go infinite. Yeah? So you see already some kind of diffusive scaling maybe appearing here. Yeah? So what is known about this process, we know pretty well. It's invariant reversible measures. Yeah? And so what turns out that if you fix some parameter rho strictly between 0 and 1, then this measure nu rho, which is the product Bernoulli measure with density rho everywhere, this turns out to be invariant for the process. Yeah? So these are all the invariant measures. Yeah? So here I excluded rho equal to 0 and rho equal to 1. I mean, for these values, the measure is still invariant, but it's not very interesting because then either you have no particles or everything is stuck with particles and then nothing happens. So these are not very interesting invariant measures. So the interesting invariant measures are really the ones that you see. So this is the exclusion process. Yeah, so I have you, for those who see this for the first time, I hope you have now some idea. And well, if you have this process, then I mean, you want to study the typical questions that we do in probability theory, maybe law of large numbers, central limit theory. And what I will focus on more today is the central limit theorem type of. Yeah? And so there's a famous observable, which is called the fluctuation. Yeah? And so to introduce this, I need some more notation. So you can study the fluctuations in equilibrium, or you can study them also out of equilibrium. And if you study them out of equilibrium, one initial measure you can take is the one that I will present now. Yeah? And so to do so, what I want to introduce is some smooth function rho naught or rho zero, yeah, which I call a profile, yeah, which is simply a smooth function, maybe C4, I think, which maps R to the interval 0, 1, and which we assume to be bounded away from 0 to 1. Yeah? So associated to such a smooth function or to such a smooth profile, you can associate a product Bernoulli measure, where now the density is not constant in space, but really depends on your profile. Yeah? So really what is happening, you're here on your line, and then you look at this function rho naught. Yeah? Let's say here's the value 1. And essentially the higher the value of the function at this point, the larger the density. Yeah? So the more chance you have to find a particle at this spot. Times 0. Yeah? And the lower the value as well, the chance to find a particle there initially decreases. Yeah? So this is kind of a standard way of looking at the initial measure for the exclusion process, which is not an environment. Yeah? And associated to this, we look at this function rho Tn, yeah, which is simply the mean number of particles at time t at position x of your process, of the exclusion process, when it started from this product Bernoulli measure associated to it. Okay. And so, so in this talk, I will either look at the process start from equilibrium or from this product Bernoulli measure associated. Anyway, once you have this, you can, essentially what is happening, I mean, the typical behavior is defined, is given by this function rho Tn of x, right? This kind of the expected number of particles you find at a certain location at a certain time. And what you can now do is to study its fluctuations around this function. So you look at the central limit theory. And this naturally leads to the so-called fluctuation field, which I defined here. So essentially what you do is you fix some smooth function h, more precisely in the Schwarz space. So this means that C infinity indicates faster than any polynomial at infinity. You may think of a function with compact support, for instance. And to this, you can associate the fluctuation field. So how does it work? So this yTn of h is what? So you sum over all space points x and z. You look at your function h evaluated at x divided by n. Yeah? And then you multiply by eta bar t of x. So what is eta bar t of x? Well, eta bar t of x is eta of x centered. So what we do, we subtract the mean of eta t of x. Yeah? So we really have a bunch of centered random variables. In particular, this yTn is also centered, as means it. And all this we multiply by 1 over square root of n. So why is square root of n? Well, assume now that h really has compact support, say compact support of size 1. Yeah? A condition that guarantees that h of x divided by n is not 0 is basically that x divided by n is less than 1. So this means x shouldn't be larger than of order n. Yeah? And since we're in a one-dimensional situation, how many points are there in the sum? There are roughly n points in the sum. So really divide by the volume of the number of points in sum. So it's really a central limit theorem type of scheme. Okay, so this is the fluctuation field. And once you've defined it, as always, you can ask yourself if as n grows, this converges to something, and if this something is Gauss. And the answer is yes, this is indeed the case. Yeah, this is indeed the case. And so this was proven by Galvis, Kipnis, and Spohn in some unpublished manuscript, and later by Harvey Shankar in the general case of ZD. And what they really showed is that the fluctuation field Yn converges in a certain space, this does not matter, to some object Y, which formally satisfies this equation. So dyt is Laplacian yt dt, plus square root of 2 chi of rho t nabla dwt. So here the function chi is given by rho t times 1 minus rho t, and w is a spacetime y. The way to formalize this, or the way to formulate it, usually is in terms of a martingale problem, which I will not mention here. But for those of you who are not super comfortable with this equation, at least in equilibrium, I mean, there's a kind of a very nice, almost rigorous heuristics. So, and I guess something like this also should hold out of equilibrium. So in equilibrium, well, what you can say, and this you can always say, y is Gaussian. Actually, this follows from already kind of from the equation, because y is a linear function of a Gaussian process, so y is Gaussian. And once it's Gaussian, it suffices to tell what's the mean and the covariance. Well, the mean must be 0. Yeah, actually, already from the construction, y and has mean 0 by construction. So what is the covariance? And basically, what's the covariance of y t of x, y s of y is rho times 1 minus rho times k of t minus s x minus y, where this guy here is the usual heat kernel. Heat kernel associated Laplacian, not the half Laplacian. In this case, the way. Yeah? And this kind of makes sense, right? Because the way I was describing the exclusion process was in a bunch of random walks. So somewhere in the correlation, the covariance, you should see the transition probabilities kernels of random walk appearing, and so in the continuum, this would be the continuous heat. This is only a formal way of writing it, because if you would set t equal to s and x equal to y, then the heat current becomes a Dirac at 0, so it's not a completely well-defined object. So it only makes sense, unfortunately, as kind of some generalized function or distribution, but that's kind of the way to think. Okay, great. So this is the fluctuation. So next, what I would like to talk about is kind of the stars of this talk, namely the occupation time and the current. So what is the occupation time? Well, it's defined here. So you fix some site x, then the occupation site time associated with the site x, gamma x, and t is the integral from 0 to t of eta bar s of x ds. Yeah? So this is nothing else than the integral from 0 to t, eta s of x minus rho s of x, where recall that this function rho s of x is simply the expectation of eta s of x. Yeah? So recentering is happening. So if you ignore the centering for some time, so imagine it would not be there. So what would be this occupation time? Well, eta s of x takes two values, either 0 or 1. It is 1 if there's a particle at x at the given time, and it's 0 otherwise. So in other words, if we would take out the centering, the occupation time would be really just the amount of time that there's a particle at x in the time interval 0 t. Or in other words, it's a recentered local time. So the way to picture it is that the occupation time is nothing but a centered local time. So looking at this formula, one thing that you also see is that you can easily write it in terms of the fluctuation field. So one way would be like this. So 1 over square root of n times the occupation time, it's really, I mean, this is rigorous still, is nothing but the integral from 0 to t of the fluctuation field, y as n, evaluated at Dirac at x. Yeah? So that's really completely rigorous. So if you look back at the definition of the fluctuation field, then this is literally what you get. Yeah? In the limit, you would obtain something. Yeah, but that's it. Yeah? So that's the first object of study, and the second object of study is what we call the current. So what is the current? So you look at a certain bond or edge, x plus 1, and what you really do is you count up the number of particles that jump from x to x plus 1, and you subtract the number of particles that jump from x plus 1 to x. In other words, the current is nothing but the net flow of particles of the bond x plus 1. Yeah. So why is this an interesting object to study? Well, it's interesting for several reasons. To some of them will come a little bit later. But let me mention maybe one thing, an object which I will not talk about much, but it's still good to mention. It's what we call the tagged particle. So what is the tagged particle? Again, many of you probably know this already, but there probably are some people in the audience that don't know this. So what's the tagged particle? Well, you look at the usual exclusion process. Yeah? You have a particle, no particle, a particle, no particle. And you start from the usual initial condition. However, you condition that at site 0, you have a particle. Yeah? So this is the orange side is site 0. Yeah? So this could be a configuration. Yeah? So this is the site 0, site 1, 2, 3, 4, 5, and so on. Yeah? And this orange particle is what we call the tagged particle. And what you would like now to understand is its evolution. So does it behave diffusively, subdiffusively, superdiffusively? And well, that's a very popular object to study. So what is now the relation between the current and the tagged particle? Yeah? So actually, you can write the tagged particle in terms of the current. Why? So let's assume the picture I just drew is the picture at time 0, and now, well, the exclusion process evolves, the tagged particle evolves, yeah? And so at time t, it will be probably at a different location. Yeah? So let's assume that at time t, maybe the tagged particle is, let's say, at position 5. Yeah? Then, I don't know, maybe at 0, there's no particle, maybe there's a particle here, maybe there's a particle here, maybe no particle here, maybe a particle here and here, I don't know. Yeah? So let's assume this is a configuration at time t. Yeah? So this means the tagged particle went from 0 to 5. So what do we know now? All the particles to the right of the tagged particle, so these 3 guys here, must still be to the right of the tagged particle, right? Because particles can't jump on top of each other. And however, so this means that these 3 particles here, they were initially to the left of 0. So this means these 3 particles have crossed the bond -1, 0, right? Or in other words, the number of particles that cross -1, 0 minus the number of particles that jump from 0 to -1 is 3. Because essentially these 3 particles that we see here, this is kind of the net flow over the bond -1, 0. In other words, what I kind of showed you is this relation. If xt is the position of the tagged particle and you fix some number a positive, then the event that xt is larger than a can be written like this. It's the event that the current over the bond -1, 0 is larger or equal than the number of particles between 0. Yeah? And that's why a typical strategy to study the tagged particle is first to study the current and then kind of try to transfer the results. Okay. So that these are kind of the 2 objects. And now let me tell you a little bit what is known results. So the first result is about the occupation time, and that's from a paper of Milton and Patricia from 2013. So their result is a bit more general, I must say. But in this context, it boils down to the following. So if you assume that eta starts from equilibrium, in this sequence of processes, so you look at the occupation time, you multiply by square root of n, then this converges in a certain sense to a fractional Brownian motion of parameter 3/4. Yeah. So that's the result about the occupation time. What do we know about the current? Milton and Claudio in 2006, So here, we don't start from equilibrium, but we start from this Bernoulli product measure associated to this profile. Yeah. And then what they do is they look at the current of this kind of macroscopic bond UN plus 1. Think of 0, 1, for instance. Yeah? And then what they showed is that its finite dimension distributions converge to a Gaussian process, and they give a formula for the covariances, which I don't want to give you. Yeah? So you've, on the one hand, the result here in equilibrium, your fraction Brownian motion parameter 3/4, and on the other hand, the result out of equilibrium to some Gaussian. And now, of course, if you want to compare these two results, you may ask yourself, well, I mean, in the setting of the second result, can we say something about this Gaussian process when we start from equilibrium? And the answer is actually yes, we can do it. Yeah? So in the equilibrium case, in the second result, the limit is again a fractional Brownian motion, but of parameter 1/4. So what is the fractional Brownian motion? Well, a fractional Brownian motion is essentially a generalization of the usual Brownian motion. The usual Brownian motion is a fractional Brownian motion of parameter 1/2. Yeah? And basically, a fractional Brownian motion is a Gaussian process such that the following holds true. Bt minus bsh square is basically t minus s to the 2h. Yeah? So if you plug in h equal to 1/2, then you will get, well, what you know from usual Brownian. Yeah? Okay. And well, I would like to still spend some time explaining this result, kind of to give you some intuition about these two processes. Yeah? So how does the fractional Brownian motion of parameter 1/4 looks like is this. So the first drawing is parameter 1/4. The second drawing is 1/2. So this is Brownian motion, usual Brownian motion, nothing more. And the last one is parameter 3/4. Yeah. So what can you observe here? Well, the first thing that you maybe can observe here, that if h is equal to 1/4, then this fractional Brownian motion stays much closer to the origin, right? It's wiggling much, much more around the origin. Whereas if h is 3/4, it kind of really goes away. The second thing that you might observe is also, well, I mean, again, in the case of h is 1/4, the sky is really wiggling much, much more around. Whereas in the case of 3/4, I mean, it essentially looks like a smooth function. Yeah? And this is actually no surprise, because by the formula that I just gave you, it essentially implies that the fractional Brownian motion of parameter 1/4 is Hölder 1/4. Yeah? It's essentially Hölder 1/4. Whereas the one of 3/4 is Hölder 3/4. So it's more regular. And I mean, this is something that you can see in this drawing. Okay. So what is now the relation between this and the current and the occupation time? Well, I mean, look at this picture of 1/4. So I said it's kind of wiggling much more around, meaning that as soon as it kind of goes up, somehow it's pushed immediately down afterwards. Yeah? In case of 3/4, when it kind of goes up, it seems that it kind of keeps the tendency of going. Yeah? Well, a way to formalize is to say that if h is 1/4, the process is negatively correlated. If h is 3/4, it's positively correlated. And this kind of makes sense if you think of current and occupation time. Yeah? The first case corresponds to the limit of the current. And the second, h equal to 3/4, is the occupation time field. And I mean, what happens with the current? So assume that you look at the current for a certain time interval, and it's kind of the current is increasing. Yeah? So this means that there are a lot of particles jumping from the left to the right over your bond that you're observing. Yeah? This means that after some time, probably not so many particles anymore at the left to the bond, but a lot to the right. So eventually this particle will want to jump back, so dragging the current down. Negative correlation. For the occupation time, however, what's happening, if the occupation time is increasing, this means that probably close to the point you're observing, there are a lot of particles, And so there's a tendency that the occupation time will increase furthermore in the future. Positive correlation. So kind of this picture, I guess, I hope makes sense. So these are kind of standard results. And before I explain what we did, what our contribution, I would like to finish kind of this part with some further observations. So the first observation is that in the result of about the current, the convergence was in the sense of finite dimension distributions. Yeah. But actually, when you're in equilibrium, then we know that you have tightness. So there's convergence in distribution. Tightness actually in the uniform topology in the space of Catlak. Yeah. But actually took quite a lot of time to prove tightness. So only 2008, Pellegrat and Setu-Raman proved tightness. And kind of this issue kind of was mentioned already by Svone in 91. We talked about convergent distribution, but tightness is for sure an important part. Yeah? So yeah, it took really quite some time to prove tightness in the equilibrium case. And the reason is that essentially, if you want to have tightness, then you need to be able to control 6 moments, at least 6 moments. Yeah? And that's not easy. And that's really not easy. Okay. So the second thing I wanted to mention is a further motivation to study these two objects is assume that we don't speed up the process by n squared, the exclusion process, but really runs at rate 1. Yeah? Then, of course, you can reformulate all the results. And the way you should reformulate them is as following. So the occupation time, if you want to rescale the occupation time properly to obtain the results that I just mentioned, you need to rescale it as I wrote down. So you need to look at the integral until time Tn squared and divide by n to the 3/2. Whereas the current, if the process is jumping at rate 1, you need to observe it until time Tn squared and divide by square root of n. So in both cases, you don't divide by the square root of the time. So there's the behavior is not diffusing. This makes it a kind of interesting object system. And moreover, observe that this n to the 3/2 is nothing but n squared to the 3/4, right? And we obtained fractional Brownian motion of order 3/4. This makes sense. And square root of n is nothing but n squared to the time scale to the 1/4. And we obtain fractional Brownian motion of order 1/4. Yeah. So this hopefully also makes sense. Okay. So this kind of closes this part of the talk. Let me come to the first results. So to motivate the first result, I mean, what we saw is that the occupation time is essentially an integrated local version of the fluctuation field, right? I mean, what we saw is essentially, well, let's consider it 0. Why not? That this thing is nothing but square root of n integral 0 t y s n Dirac at 0 ds. So the occupation time locally, formal way, can be written in terms of fluctuation. So you may ask yourself if the same also holds true for the current, and the answer is yes, at least globally. Yeah? And to formalize this, we need to look at the current field. Yeah? Which we introduce, well, S1 introduces fields. Yeah, so what I wrote down here, this is the current field. So again, you take some Schwarz function H, think of a function of compact support, for instance. Yeah? We sum over all space points X. We look at H evaluated X divided by N, and we multiply it by the recenter, by the centered current. This is the meaning of the bar. Of the bond x plus 1 and divide by n. Why we divide by n, this will be in a moment, hopefully. And this whole thing, again, we divide by square root of n, where again, the square root of n is essentially the number of points you really observe in the sum, right? If H would have compact support, then the number of points in the sum would be really important. So this is kind of a global version of the current. Yeah? And indeed, it's possible to give a direct relation to the fluctuation field. And the way it works is the following. So if you look at this joint process, fluctuation field, current field, so then this converges in a certain sense to some process yt, jt, where this yt is really the fluctuation field, the limiting fluctuation field, and jt, you get the limiting current field, and these two objects are related in this way. So this means yt of g minus y0 of g is the current field evaluated as a derivative of g. Yeah. Okay, so this is the result. That's the first result, which was out of equilibrium. And what I would like now to do is to argue why this is the case. Yeah, so I essentially give a sketch of the proof, which is almost rigorous, I would say. Yeah. So let's sketch of the proof. And well, again, so I'm sorry. So most of the things that I say are probably known to the experts, even so the results are new. Okay, so what you see is kind of the following magic identity. If you look at the current between x minus 1 and x, and you subtract the one from x to x plus 1. So, I mean, what is happening here? Say, here here's your point x minus 1, here's your point x, here's your point x plus 1. So to calculate the current of the bond x minus 1x, so what do we do is, every time there's a particle jumping from x minus 1 to x, we count plus 1. Every time there's a particle jumping from x to x minus 1, we subtract 1. Right? And the same happens essentially for the current between x and x plus 1. Every time there's a particle jump from x to x plus 1, we add 1. And every time there's a particle jump from x plus 1 to x, we subtract. The first thing, the left picture is j of x minus 1x, the right picture is j x plus 1. However, now we subtract j of x plus 1, so we need to switch the signs. So the plus becomes a minus and the minus becomes a plus. So this becomes a minus and this becomes a plus. Yeah? So really what is happening here is every time there's a particle jump on top of x, you count plus 1. Every time there's a particle jumping away from x, you subtract 1, right? So in a sense, this difference here, j of x minus 1x minus j of x plus 1, is kind of what you essentially do is you compare the number of particles that they are at position x at time t with the number of particles that were there at time 0. So in other words, you get this magic identity, which still holds if you center everything. Yeah? And essentially, this identity is key identity to prove the result. So once you have this, well, you're in very good business, right? Because, so let's remember, so what is the definition of the occupation time field? Is the sum g of x divided by n times eta bar t of x minus eta bar 0 of x, right? So this is just the definition of the fluctuation field. And so now this guy here, you replace using this magic identity. X minus 1x minus j x plus 1 of t bar. Yeah. And then what you do a summation by parts. And essentially you shift the derivative, this discrete derivative, to the function g. And then you essentially so g of x plus 1 divided by n minus g of x divided by n j bar of x plus 1 of t. Yeah. If I want to have a discrete derivative here, I need to multiply this by n, right? To really have the discrete derivative, so I need to divide by n. Yeah? And if you look carefully, this is really the fluctuation field at the discrete gradient of G. And from this, essentially, the result follows. Now you use some approximations, but from this observation, essentially, the result follows. Okay. So this is the first result, giving a relation between the fluctuation field and the current field. Yeah? And so again, so essentially shows that globally the current is a function of fluctuation field. You can also show that globally the occupation time field is a function of the fluctuation field. And now what you may ask, what is very natural to ask, what is the relation between the occupation time and the current? I mean, globally they seem to be related, so for sure they're also locally related. So it's a natural question to ask. Yeah? So what is the joint behavior of the current and the occupation time? And in least equilibrium, we have the following result, which is a corollary of one of our results. It's the following. So if you start the process from equilibrium, then the sequence of processes where first coordinate is the current between -1 and 0, and the second is the occupation of the site 0, they converge to some joint process, J and gamma, where J and gamma are actually independent. So this result shows that even though, at least in equilibrium, even though globally current and occupation time you can write in terms of the fluctuation field, locally they're independent. Yeah? And this came a little bit as a surprise to us, so I will sketch the proof, and the proof is not so difficult. This came a bit as a surprise to us because, I mean, the way you calculate the current is essentially by looking at the particles that are around your point 0, and the way you calculate the occupation time is also by looking at the particles that are around the point 0. So actually there should be some dependence. Yeah? However, this result showed that kind of this intuition that we had is simply wrong. Yeah? And the proof is really, really simple. So let me sketch it at least for you. So how does the proof work? I mean, you use some kind of a moral identity. So morally, what is true is that the current between -1 and 0, you can write like this. It's the sum of x greater or equal than 0, eta t of x minus eta 0 of x. Yeah? So why does this perfectly make sense? Well, what you do in the current, you look at the net flow of particles of the bond -1, 0. The number of particles jumping from -1, 0 minus the one jumping from 0 to -1. On the right-hand side, what you could do is you could split the sum into 2. If you do this, what you have is that the number of particles that are to the right of 0 at time t minus the number of particles that were at the right of 0 at time 0. Yeah? If this number is positive, so this means that in total, more particles cross -1, 0 than they crossed 0, -1. If it's negative, the other thing is the opposite is true. Yeah? So this perfectly makes sense. This is only a moral identity because, well, the left-hand side is some random finite number. It perfectly makes sense. The right-hand side in general will diverge. It doesn't make sense. Yeah? So the right-hand side makes sense if you start with a finite number. But anyway, I mean, something like this should be true, and you can, using approximation arguments, you can show that something like this is indeed true. No? But well, for the sake of the talk, let's assume this is completely rigorous. Yeah. And then, I mean, if you want to show independence, I mean, one thing you can do is to compute the covariance at least. Yeah, so let's do this between the current and the occupation time. Yeah. So what is this? Using our moral identity, that's the sum of x non-negative, integral 0 t expectation of eta bar t of x minus eta bar 0 of x times eta bar s of x. ds. Yeah? Where so this term comes from this formula, and the second term, well, comes from the definition of the equation. Now, if you're in equilibrium, it's not so difficult to compute this. This is rho times 1 minus rho, the sum of x non-negative, integral 0 t, pt minus s of x, minus ps of x ds. And now, well, you can do a change of variable argument to show that this sum is actually 0 for any x. So these two things are uncorrelated. Since they converge to something Gaussian, they will be independent. Okay. Okay. So, contrary to at least our intuition, these two objects are independent in the limit. Yeah? And now, I mean, so now, I mean, so this result was now in equilibrium. Now you can ask yourself if this independence is coming from the dynamic itself, or is it kind of some kind of magic identity that happens because you started from equilibrium. Yeah? And what turns out to be true is that they're independent because of some magic that happens because we start from equilibrium. Yeah? So if you start from some general measure, then the current occupation time locally are correlated, not independent. Yeah? So this is the content of this result. So if you start the exclusion process from this product Bernoulli measure associated to a profile, yeah, then this joint sequence of processes where the first coordinate the current, the second is the occupation time, they converge in distribution to a Gaussian process where the two coordinates J and gamma are in general not independent. Of course, you may find some very specific function, some very specific profile rho where they're independent, but in general, they're not independent. So we have well, precise formulas for the correlations, for the covariance, which I don't want to write down here. And so this really shows that kind of this result, this equilibrium result is, well, it's sense because essentially some magic happens. So it's not something that is coming from the system itself. Yeah. So until now, I've been a bit sloppy when, I mean, I didn't talk much about the mode of convergence. So let me just say 2-3 words about here. So here we actually, so this is, I mean, we are still writing this up, but we think that we have tightness also for the current, for the occupation time and for the current. For the occupation time, it's not so difficult. But we think that we also have tightness for the current, which is a non-trivial issue because you need to estimate higher moments. Yeah? And as I said earlier, this was an issue already in equilibrium. And it turns out that equilibrium proof is very much based on looking at the process at equilibrium. It seems impossible to generalize it. So you really need to make your hands dirty and try to get a handle on higher moments of it to get really tight. Okay, I think I have maybe some 5, 6, 7 minutes left. So let me say some words only about the proof. Yeah. Again, some of the heuristics I give are probably known to the experts, but anyway. So what you want to show is that essentially both of these coordinates converge to Gaussian processes, and okay, you would like to compute the relation between these Gaussian processes. So let us first focus on gamma. So what I said so far is that gamma is some kind of integrated local version of the fluctuation field. Yeah, something like this. And now, of course, I mean, your idea is, well, let's n tend to infinity and hope that this converges to something nice. And well, we know that the fluctuation field converges. However, what I was already mentioning is that the fluctuation field is not a function. It's not an L2 function, continuous function, or something like this. It's a distribution, it's a generalized function. So it does not make sense to evaluate the fluctuation field at a fixed point. Yeah. So really evaluating at the delta at 0 does not make sense. So this means that if you kind of want to have the relation, this relation here, in the limit, you need to do some kind of approximation procedure. And the way you do the approximation procedure is essentially you approximate the delta 0, you kind of smoothen the delta 0 out. Yeah? And so this is the idea. So the idea, smoothen out the delta 0. Smoothen out the delta 0. The Dirac at 0. Yeah? And the way it works is the following heuristics. Is that square root of n, the occupation time. Yes. Okay. So this is n times eta bar s of 0 ds. Yeah? So here you essentially see the Dirac at 0. And now the idea is you want to smoothen it out. And the way to smoothen it out is to take a spatial average. Of course, you need to justify this, but this is something you can do. Eta s of x, yeah? And then it really turns out that there's nothing but the occupation time field at this function iota epsilon of 0, where this function is the indicator function of the interval 0. Epsilon, which may be not smooth, but is much better behaved than a Dirac. Yeah? And essentially the big challenge here is to make sense out of this approximation. Once you have this, then you're in a pretty good shape. Yeah? But essentially what you need to show is that you really can smoothen out the delta 0. So what happened, this first approximation is we smoothen out the delta 0. And this is the content of a replacement lemma, which of course already exists in the equilibrium case, and which turns out to be true also out of equilibrium. Yeah. So the way to formulate is you fix yourself some kind of a time window, some epsilon, yeah? And then you look at this kind of replacement, which depends on space and on time. Yeah? Space and time, which is eta 0 minus rho s of 0 minus 1 over L, the sum from 0 to L minus 1 of eta y minus rho s of y, where you think of L being given by epsilon n. Yeah. So if this eta would be here really eta s, yeah, then it's really literally what I just wrote down in the approximation. Yeah. So this is the term you essentially have, let's say with an s, and you would like to approximate this by the sum. Yeah. And this lemma says that indeed you can do this in L2, yeah, to a sufficiently good degree. Yeah. So for any S and T, this kind of second moment is bounded from above by some constant times T minus S epsilon to the 3/4 over N. Yeah. This is a kind of a famous result in equilibrium. It turns out it's also true out of equilibrium. So here we proved it really for the nearest neighbor simple exclusion process, but we checked, I mean, we are, let's say 99% sure that the same can also be done for VASEP, say, with drift of the order 1 over n. In the non-nearest neighbor case, it should you should be able to do this if your transition probability has third or fourth moments. I'm not completely sure. We use this local center limit theorem for that. For this, you need moments of order 3 or 4. Yeah. So this is probably true also not only for the specific process that we are looking at. Yeah? And once you have this lemma at hand, I mean, all this approximation essentially becomes trivial. Yeah? Okay, so this is about gamma, and I'm seeing that I'm running out of time. So then just let me say, spend 1 or 2 minutes on the tightness of the process J. So what about the tightness of the process J? Well, in equilibrium, J is converging to a fractional Brownian motion of parameter 1 over 4, right? So in a sense, what you expect if you want to use some kind of Kolmogorov change of type criterion of tightness, what you expect is that you have an estimate of this order. Actually, there should be probably absolute values, I guess. You have an estimate of this order. So if the exponent here should be larger than 1, you should choose p equal to 6, right? Because you don't want to deal with this absolute value. So this would be kind of the optimal thing. And so first of all, I mean, dealing with 6 moments is pretty nasty. And second of all, so what it turns out, I mean, if you want to prove tightness and you're only interested in kind of uniform convergence and uniform topology, all you need to have on the right-hand side, you need to have an exponent that is larger than 1. It must not be p over 4 for p equal to 6. It's 1 plus epsilon would be enough, and you're allowed to choose your p. However, it turns out that probably p equal to 6 is the optimal exponent. However, what this also means, if you deal with 6 moments, it's a quite high moment to deal with. And if you want to have a nice exponent which is larger than 1, then you need to show that certain cancellations are happening. So when you kind of write the thing out, you obtain certain alternating sums. I would need to go much more detail to it. And you kind of would need to show that these alternating sums cancel out quite nicely. So it seems to be a complete mess. That's why it was also open the equilibrium case for such a long time. But here was kind of the observation that Tiecheng did. So, and I must admit that I first thought he's completely crazy when he told me this. But it kind of turns out to be the right thing. So what was his observation was that, well, dealing with 6 moments is difficult. Establishing the good cancellations for the 6 moment is difficult. For the 6 moment is difficult. It's too difficult to us, actually. It's difficult. So one thing you could do is, instead of estimate 6 moments, estimate higher moments, right? Because what you kind of expect, the higher the moment, kind of the better your estimate gets. So this also means the more rough you can be in all of your estimates. Yeah. And it turns out that 10 moments is probably the optimal one. So better estimate 10 moments. Moments of order 10. Moments of order 10. Yeah. So this seems to be a bit not very intuitive, because the higher the moment, the more difficult it should get. But you can convince yourself, once you're dealing with 6 moments, you're already dealing with a lot of sums, which is a complete mess. So you need to find some kind of general way, and then why not go to higher moment where you're allowed to kind of be much more rough in your estimates. And this seems to be kind of a good thing to do. So right now we are in the process of writing this up, but it really seems that we're very confident that it's working. And, I think with this, I guess my time is up, and thank you very much.
Hi, Dirk. I'm not sure if Claudio is gone and if I am supposed to share. Milton, do you know if?
Yeah, Claudio's gone.
But okay, so did he told you to continue, or is it me? Because you have the microphone, so that's why I'm asking.
Yeah.
It's you? Okay.
Yeah.
Okay.
Okay, so let's go. Yeah, okay. So okay, so first some clapping of hands for Dirk. Okay. Is this thing working? Do you hear me? Yes.
I can hear you.
Okay. So now questions from the audience. So do you have any question? No questions here. I don't have. I cannot. Let me see if I can see the Zoom
I have a question, Milton.
Okay.
Can I ask?
Yes.
It is just okay. So first, I like very much this talk. In fact, this subject I discussed this with Tertuliano a long time. I think maybe more than 10 years ago.
Oh, really?
And
Okay.
yes, and I think it's very, very nice. But one question, Dirk, okay, I have several, but okay, let me start. When you say out of equilibrium, you always mention that you are starting with this Bernoulli product measure with a certain profile. Can you do this for more general measures?
I think certain things, yes. So what we need is to have good estimates on the correlations. So the good second correlation is the second estimate, right?
Mm-hmm.
We have this, we can do this. We don't use entropy or something like that.
Okay, good.
This,
And another question is this, because you have this okay, it's my second question. Maybe I just let everybody, someone else ask another question. But this relationship that you have between the target particle, the current, and the density of particles that you show to us on the picture, because you say that if the target particle is at 0 and then it moves, then it means that this, that this has a relationship between the current, the flux through -1, 0, and the particles that are just before the target particle. So this is, in order to have this is crucial to be in dimension 1. So if, does any of these results go to higher dimensions?
The relation between the current and the target particle? Yeah.
If some of these results, if you can avoid, because to have this relationship, you need to be in dimension 1, right? But can you avoid, can some of your results be obtained in higher dimensions without using this relationship?
So what we never used the relation to the target particle. This was just at the motivation. So I think first you establish a result for the current, and then you use this result as an input for the target particle. So this, how you would do it in higher dimensions, I don't know.
Okay. But the rest is should hold in any dimension.
I would need to check it. Some things may be really specific to the dimension. For instance, so I'm not sure how this moral identity, this is almost rigorous, as you know. I'm not sure, for instance, how this holds. So this kind of identity plays a big role, because it kind of already tells you a guideline of how to approximate the current. So I'm not sure if there's some some replacement for it in higher dimensions.
Higher dimension, okay.
I'm not sure if I already saw the current in higher dimensions. Have you?
Yes.
This relation makes sense if you look at the current on through a line, for example.
Yeah,
that's true.
Exactly.
That's true.
Yeah,
that's true. Yeah, that's true. Maybe that's probably that's the object that you should look at, right? In higher dimensions. Yeah.
Okay, thanks.
Then I'm pretty optimistic. So most of, we use this kind of stuff as an input, but many of the estimates, I don't think that they're very much related. We didn't use so many magic identities. This was one.
Well, maybe I could, thanks to Dirk for the nice talk. Maybe I could comment that for the occupation time, let's say in 3 or more dimensions, it should just be Brownian motion.
Exactly.
Right.
Exactly. So I think in this business, maybe for the occupation of 1 dimension, maybe probably one of the more interesting regimes, right? Because you don't get diffusive behavior. You don't get the normal Brownian motion. Exactly.
Even in 2 dimensions, just the scaling just has a log in it. That's all.
Yeah.
Did you use attractiveness at all?
No, not at all. No.
So the initial condition that you have, the rho not the profile, is it strictly bounded between 0 and 1, or?
Yeah. So for this kind of replacement lemma, we needed this. Probably you can relax it, but where's this? For this replacement lemma, we needed it. but maybe there you can also make do without it, but simplify the proof. So I guess you can relax this a little bit. You can probably relax it, but it was much more convenient.
Maybe I could just comment there. I did some work earlier about the fractional Brownian motion for the occupation time. I think it's in 2000. Yeah, also probably. So there, one is using negative association and positive association, and some Newman central limit theorems and things like that.
Okay.
Specialized. So what you're doing is more general. So it's very nice what you're doing. But maybe a comment.
Cool. Thanks a lot. I will have a look. 2000, more or less 2000, right?
Yeah.
Cool. Thanks a lot. I will have a look.
Okay, so
Pablo here.
Okay, good.
Very nice talk. I like that identity between the current and this density is something. No, I was wondering about the non-nearest neighbor case, because here you're using nearest neighbor, right?
Exactly, but I think a lot of the things should go almost without shame.
But the target particle in that case, so the current is still order t to the 1/4 in that case?
Yes.
Okay.
I don't know how then. I don't know how the relation. I didn't think about this. The tech particle changes. I mean, as I was saying, we didn't say any. About the tech particle, I use it here as a motivation.
Okay, no, because the target particle in that case is Gaussian, right? It's like t to the 1/2. When
in this particular case, I think tech particle is not diffusive. The current, so like t to the 1/4.
But this is a nearest neighbor. But as soon as you lose the nearest neighbor, then the target particle goes to Gaussian, to t to the
okay.
half. Now this was the reason I was asking.
I see.
Okay. Thank you.
Thanks.
Okay, so any more questions? Just a quick comment. At some point, you will have to show us why estimating 10th moment is easier to estimate 6 moments, because this looks very counterintuitive. And for all, I think I speak for most of the audience. I mean, we know how difficult are to estimate 6 moments with our more pedestrian methods. So I cannot even imagine how difficult could be the 10th moment. So it's I
mean, when Tiecheng first proposed it, I also thought, I mean, he must be out of his mind to propose it. But the reason, I mean, of course, second moments are nice. Fourth moment gets already a little bit more messy, but maybe you can still work out things by hand. And 6 moments, I mean, it almost becomes so ugly. I think if you would write down everything very precisely, all the sums, I mean, you would make mistakes. So you need to find a nicer way to write down things. And then at this point, it doesn't matter how high is your moment. I think that is kind of the idea. I mean, the work you have to go from 6th moment to moment of order 236s. It's minor. Not nice.
Okay, well, so let's thank again Dirk for this wonderful talk. So see you again on the next week, right?
Thanks a lot. Bye-bye.
Bye.
Bye-bye. Thank you.